Okay, so we've set the channels up, we've validated everything's working, we've set the sensitivities, and now we're going to head into the impact scope book. You'll notice we're stepping over calibration. We can calibrate the sensors, but for modal analysis, generally speaking, shapes are relatively scaled, arbitrarily scaled, and therefore we're not really interested in calibrating our sensors. We can do, but we're not interested. So we go to impact scope, and in here I can then check the ranges on the transducers, and I can, for example, change the ranges on the transducer. So I've got two screens here which are showing me both channels. If I do some impact, you can see impacts coming through on the left. I'm also showing it again in detail in this view, and I can change the detail view to show the response measurement. And the response, I'd need to come over here and tap this one. When I tap this one, you can see the response, which is being measured by the vibrometer on the right hand side, the impact on the left, and then obviously detail view here for the response measurement. As I tap the target, it does move around under the vibrometer. I have to keep putting it back into position. Okay, it's now on a relatively light suspension system, which is this piece of foam. That's intended to give a free boundary condition. It's never fully free, but we do our best to do that. What I'm also looking at when I'm tapping with the indicative levels of taps is, have I got the ranges set up on the transducers properly? So on the response transducer, I've got 10 volts range. I'm getting lots of signal. I'm getting a nice green level on that bar indicator. For the impact, the harder I hit it, the more energy I get. At some point I can overrange it. If it goes orange, red, that's not good. Okay, but I'm hitting it way too hard. I don't need to hit it that hard. It's not about how hard you hit it. For a linear system, the response will always be a function of the level of the excitation. Of course, not all structures are linear, but we can approximate many to be that. So that's the level set properly. I've also got some specifications on bandwidth and spectral lines, resolution, which is the reciprocal of the acquisition time. It's presently 4 Hertz. I'm measuring for 1/4 of a second. I can change some of these parameters in the scope. I probably want a little bit better resolution, so we'll go for perhaps 0.5 Hertz resolution, which is going to give me 2-second acquisition time. I think that I'm interested in up to around about 100 Hertz perhaps, but I'm going to measure at 512 Hertz sample frequency, and that's probably a sensible setup. Now we're going to move to the impact setup workbook, where there are some specific sub-workbooks up here that help us specify things like triggering, the bandwidth of acquisition, and so on. So first one is triggering setup. I'm in the start the scope over here, and then I can do some example impacts, and you'll see them come through on the scope at the top of the screen. When I've done some that are sensible, like I'm expecting to achieve, I'll hit stop, and it will capture those few impacts in here. I'm trying to set the trigger threshold, which I can do here interactively by dragging this slider up and down. It tells me the trigger threshold here is 2.8 times 10 to the minus 3 volts. I can show that in engineering units as well instead if I wish. And you can see that essentially when the impact begins, I can see the rising voltage level here. So if I zoom in a little bit on these units, for example, go from minus 0.2 to 0.2, we'll see the impulse, the nature of the impulse here zoomed in. I'm looking for this to be a perfect impulse, and then that would give me a very flat frequency response across the frequency range. Of course, mechanically I can never achieve that. I end up with some kind of pulse. I'm trying to avoid a double impact ultimately, but really I'm in this worksheet interested in what should I set the trigger threshold to be, and how much pre-triggering do I need to make sure I capture the entire pulse, which includes, you know, all of this up to the peak. Okay, so it suggests to me some settings here which I can either accept, or since I've done this before and already taken these, I can not accept them. I can manually enter them if I want to change them, but basically I've got a trigger threshold of 0.28 volts and a pre-trigger of 0.001 seconds. Verify the trigger settings. I press the start button down here, and then I'm looking at this hardware triggered force signal down here underneath. So go back to my sample, tap it, and if it's going to properly triggered, it's going to capture that impulse, and that impulse should be at the start of the waveform, which is over here to the left hand side. Actually, I think I need a bit more pre-triggering, so I'm going to stop this, I'm going to reduce that by a factor of 10. I'm going to that's gone to 0.09. I'm going to restart. Now when I strike the structure, you should see now that I'm capturing the full impact event. So there's just a little bit of time here. I'm capturing the entire waveform, whereas before I was cutting off the front edge. Okay, so that's now good. We can stop and go to the bandwidth mini workbook. Now if I hit start over here, this is about making sure my tip stiffness is good, giving me a good duration impact and therefore a good frequency frequency excitation. So I try and do a very clean impact, and you can see that this is the power spectral density of the excitation. Really I'm looking for that to be flat across. It's very hard. It's a function of how well I strike it, the nature of my boundary conditions, the suspension, the nature of the sample dynamics and various other things. So this isn't easy particularly to get right, and at the moment I'm not doing a very good job, but if I keep trying and get a good clean impact, hopefully you can start to see that I'm getting reasonable excitation across this frequency range up to, you know, probably a couple of hundred hertz. Try again. Yeah, this is not optimal, but I'll accept it and go to windowing. Here I'm going to be able to define, for example, a force exponential window on the input and an exponential window on the response. Again, I can start the measurement, do an impact, and I can see measurement before windowing is applied. I'm looking for this to be 0 by the end here, such that it satisfies Fourier requirements to do digital transformation into frequency spectra. And on the response side, you can see here, this is what I'm expecting to see, some sort of exponentially decaying response dominated by the fundamental frequency. You can see here probably some higher order modes or natural frequencies on top of that. And again, the PSD of the input signal, the PSD of the response, and that's my FRF for the measurement, which basically shows that I've got a peak first bending mode at around about 24, 25, 26 hertz. Okay, there is another mini workbook up here called driving points. This allows me to check that I'm not trying to make a measurement on a nodal line, for example. Typically we don't need to use that with simple structures. We know where we need to do impact and we know where we need to measure responses, but that is available for more complicated structures. And then I would go to the measure sheet and start the measurement campaign, roving the hammer around the structure, measuring several averages at each point, building up an FRF set that I can then go on to do modal analysis processing. And that's it for this video.